Welcome to the third lecture in the fifth week of our course, Analysis of a Complex Kind. Today we'll learn about the fundamental theorem of calculus for analytic functions. Remember the conclusion of the fundamental theorem of calculus. Given a continuous function f and an antiderivative, so a function uppercase f whose derivative is lowercase f, we can evaluate an integral from a to b of f of x dx by taking the antiderivative, evaluating it at the upper bound, and subtracting from that the value at the lower bound. The question is there a complex equivalent for this theorem? Let's start with the definition. Given a domain D and a continuous function in that domain, we say that a primitive of that continuous function is an analytic function uppercase f whose derivative is equal to lowercase f. So pretty much that's the same concept as an antiderivative. Sometimes the word antiderivative is used as well, but I wanted you to know that primitive is a term that's typically used in the complex setting. So again, an analytic function f whose derivative is lowercase f is called a primitive of lowercase f and d. Here's a theorem that resembles the consequence that we begin with of the fundamental theorem of calculus. Suppose lowercase f is a continuous function on the domain, and it has a primitive uppercase f on that domain. Then for any curve gamma in the domain, if you integrate lowercase f over gamma, you can evaluate that integral by taking the primitive and evaluating it at the endpoint of gamma, and subtracting from that the primitive evaluated at the initial point of gamma. So look at this picture. We have a point A, which denotes the initial point of all of these curves I drew. I drew three curves, a green, a red, and a pink one. A is the initial point of all these curves. B is the end point of all these curves. So there are three different curves. No matter which one I integrate over, the integral of f of z dz is going to be f at the end point, so that's B, minus f at the initial point, so that's what I denoted with uppercase A. So the integral only depends on these 2 points A and B, and not how the curve got there. The big sort of hidden assumption is that this only works if the function f has an antiderivative. You can't typically say that the integral over gamma, f of z dz, only depends on where the curve gamma starts and ends. If f does not have a primitive, this is just not going to be true. So under what assumptions does f have a primitive? It seems to be a really important thing to know. When does f have a primitive? But first let's look at some examples. Suppose gamma is the line segment from 0 to 1 plus I. There's 0 and there's 1 plus I, and so here's this line segment from 0 to 1 plus I. And let's look at the function z squared. The question is, what is the integral over gamma z squared dz? Well, the function z squared has a primitive in all of c, namely 1/3 z cubed, because the derivative of 1/3 z cubed is 3 times 1/3 z cubed, which is z squared. Therefore, the integral over this curve gamma of z squared dz can actually be written as the integral from 0 to 1 plus I z squared dz. So this notation sort of indicates we don't really care how gamma got from 0 to 1 plus I, because the integral doesn't depend on how it got there. And we know by the theorem that it's the primitive f evaluated at the end point of gamma minus the primitive evaluated at the initial point of gamma. But the end point of gamma is 1 plus I, and the initial point of gamma is 0. So this is gamma of b and gamma of a. But the antiderivative, or the primitive evaluated at 1 plus I, is 1/3 1 plus I cubed, and at 0 we get 1/3 times 0 cubed, which is 0. 1/3 times 1 plus I quantity cubed is 1/3 times, and now we multiply through here, 1 plus 3i plus 3i squared, which is minus 3, plus I cubed, which is the same as minus I. And when you simplify, you find that's 2/3 times minus 1 plus I. Let's look at another example. Can we evaluate the integral of 1 over z over the circle of radius 1 using a primitive? So what is a primitive of 1 over z? Well, we do know that the logarithm function has 1 over z as its derivative, but not in all of c. The logarithm function log z is only analytic in c minus the negative real axis. We needed to cut open the plane, because across that negative real axis, this function log z wasn't even continuous. And so we do not have an antiderivative of 1 over z in the entire complex plane, because if we did, what would this integral be? If we had an antiderivative in the entire complex plane, the circle of radius 1 is a closed curve, which means its initial point is the same as its end point. If we had an antiderivative and evaluated that at the end point and subtracted from that the value at the initial point, because end point and initial point are the same, the integral will be 0. But we know this integral is not 0. We have actually found this integral. It is 2 pi I. So that shows this function cannot have an antiderivative. And we know that. Log z is an antiderivative, but not in all of c. We need to cut the plane open along the negative real axis. So how do we evaluate the integral then? Well, let's take another curve, gamma tilde. And the gamma tilde be the part of the unit circle that starts just below. So there's gamma tilde of a, and then gamma tilde goes all the way around the unit circle and ends just above the unit circle. That's almost the same as integrating over the whole unit circle, but just missing a really, really tiny piece. And we can make the tiny piece that's missing as small as we want to by just moving these points really, really close to the negative real axis. So this is a really good approximation of integrating over the entire curve gamma. So the integral over gamma, 1 over z dz, is almost the same as the integral over gamma tilde, and we can make this as good as we want to. But when we integrate over gamma tilde, for all where gamma tilde is concerned, we have an antiderivative. The antiderivative of 1 over z is log z. So we can take the logarithm, evaluate it at gamma tilde of b, subtract logarithm of gamma tilde of a. So what is the logarithm at gamma tilde of b? Gamma tilde of b is a point just above the negative real axis, and above the point where that circle would normally intersect the negative real axis, and that is -1. So gamma tilde of b is a little bit north of -1, just a tiny little bit. So what's the logarithm of that? Remember, the logarithm function is defined as log z equals the natural log of the absolute value of z plus I times the argument, uppercase argument of z. On the unit circle, the absolute values are all equal to 1. So natural logarithm of 1 is 0, so you end up with just I times the argument of z. For a point just above the negative real axis, the argument is about to be pi I. In other words, the logarithm of gamma tilde of b is pretty much pi I. For a point just below the negative real axis of -1, the argument is negative pi I. So we're subtracting negative pi I, and pi I minus pi I is 2 pi I. These two approximations here can be made as close as you wish by moving these 2 points closer and closer to the negative real axis. In other words, we can conclude that the integral z equals 1 over z dz is 2 pi I. Well, we knew that. Let's look at another example. Suppose gamma is any curve in the complex plane from I to I over 2. So I could clearly simply go along the imaginary axis, but I could also go a really complicated path, or a path like this, any path. Suppose you wanted to integrate e to the pi z over any such path gamma. E to the pi z has an antiderivative, namely 1 over pi e to the pi z. So that's a primitive of e to the pi z. Therefore, we can take the primitive and evaluate it at the end point of any of these curves gamma, and subtract from that the value of e to the pi z at the initial point, which is I. So we get 1 over pi times e to the pi I over 2, and subtract from that 1 over pi times e to the pi I. But e to the pi I over 2, that's I, and e to the pi I is negative 1, so that we get 1 over pi times I plus 1. Let's look at a final example. Suppose gamma is any path in C from minus pi I to pi I. So let's say minus pi I is right here, and pi I is right there, then gamma is any path from down here to up there. It doesn't really matter how it gets there. What we want to find is the integral of cosine z dz over this path. Well, cosine z has a primitive in C, namely sine z. And so all we have to do is take that primitive and evaluate it at the end point pi I, and subtract from that its value at the initial point minus pi I. So we need to evaluate sine of pi I and subtract from that sine of minus pi I. Let's do that. Well, sine of pi I minus sine of minus pi I, we notice that the sine function is an odd function, even the complex version of it. So this negative sign can be pulled outside of the sine function. Together with this negative sign, we get a plus. So all we have to find is 2 times sine of pi I. Now remember how the complex sine function is defined. Sine of z is defined as e to the iz minus e to the minus iz over 2i. Together with the 2 in front of it, we get 2 times e to the I pi I minus e to the minus I pi I divided by 2i. The 2's cancel out. We can bring the I to the numerator as a minus I, and we're left with minus I times e to the I squared is negative 1, so e to the minus pi minus e to the minus I squared is 1, so e to the pi. We can pull the negative sign inside and find this is I times e to the pi minus e to the minus pi. So having a primitive is wonderful. A function that has a primitive has integrals that can be evaluated over paths really simply. We're just taking the primitive and evaluating it at the endpoint minus the primitive at the original point of the curve. So what functions have primitives? Here's Gorzat's theorem. Given a simply connected domain D in a complex plane and an analytic function in D, this function f has a primitive. The big assumption in here is that D needs to be simply connected. Moreover, a primitive can be found explicitly by picking some point in D, z0, and letting f of z, uppercase f of z, be the integral from z0 to z of f of w dw. So integrate f over any path from z0 to z, and the integral will not depend on the path because we have a primitive. And so therefore that's how you can find a primitive. So the integral is taken over an arbitrary curve in D from z0 to z. So the big statement in this theorem is that if D is simply connected and f is analytic in D, then f has a primitive. I want to show you the steps for this proof. I will not show you the entire proof, but the steps required to prove this very important theorem. The first step consists of showing Morera's theorem, which says the following. If f is a continuous function in a simply connected domain, and if in addition for any triangular curve gamma, the integral over gamma f of z to z is equal to 0, then f has a primitive. So this is a theorem that gives us assumptions that show that f has a primitive. By a triangular curve, we mean something that looks like a triangle. So it has 3 straight sides, fits into D, and it's a triangle, and we always orient it counterclockwise. So if the integral over gamma f of z to z is 0 for any triangular curve gamma, and D is simply connected, then f has a primitive. So in order to conclude Gorzat's theorem from Morera's theorem, what we have to show is that if f is analytic, then the integral over any triangular curve is 0. And indeed that is true, and it's called Cauchy's theorem for triangles. It is in fact true as follows. For any triangle T that fits into D, including its boundary, the integral over the boundary of T f of c to z is 0, given that f is an analytic function in the domain D. I'll give you a few details of the proofs of these two theorems. Here again is an exact statement of the Cauchy theorem for triangles. Suppose D is an open set. We actually don't need it to be simply connected for the Cauchy theorem for triangles. And suppose f is analytic in D. Suppose T is a triangle that fits into D, including its boundary. So it wouldn't be allowed for one of the corners of the triangles to be on the boundary of D. It has to really fit into D as you see in this picture. And suppose boundary of T is the boundary oriented positively, so counterclockwise. Then the integral over the boundary of T of f of c to z is equal to 0. The proof idea is as follows. You start by subdividing this triangle into 4 equal-sized triangles. And then notice, I can integrate around this triangle, and integrate around this triangle, and this triangle, and also around this triangle. But if I do so, along this side, for example, if I integrate in the lower right-hand triangle, I integrate it this way, but in the green triangle, I'm integrating over the side that way, and the two integrals will cancel out if I add them all up. So the upshot is that the integral over the boundary of T is the same as the sum of the 4 integrals over the boundaries of the smaller triangles. We then use the ML estimate. Remember, that was the estimate for the absolute value of the integral, and that was bounded above by the integral over the boundary of T of the absolute value of f of z dz. And so if f of z was less than or equal to some constant m, that was less than or equal to m times the length of the boundary of T. So that's the kind of estimate we use. And if we can show that something on the right-hand side goes to 0, well, then this on the left-hand side must go to 0 as well. We keep subdividing and use the ML estimate together with delicate estimates on the length of the boundaries of the triangles and the fact that f is analytic inside the triangle to, in the end, show that this integral is smaller than any constant epsilon that's positive, therefore must be 0. As for the other theorem, which was Morera's theorem, let me remind you what that said. If f is a continuous function on a simply connected domain, and if the integral over any triangular curve gamma f of c to z is equal to 0, then f has a primitive. Here's the proof idea for that theorem. First, we show Morera's theorem in a disk. The proof actually is not hard in a disk and very much resembles the proof of the real-valued fundamental theorem of calculus. The hard part is to extend the result to arbitrary simply connected domains, so not a disk but some arbitrary simply connected domain. That part is not that easy. It requires the use of Cauchy's theorem for simply connected domains. We'll discuss Cauchy's theorem for simply connected domains in the next lecture. We'll also discuss the Cauchy integral formula in the next lecture.